Welcome everyone. So this week we're happy to have a peer review to talk about something about multiplicative vertex algebra and the one crossing.
Yeah, great. Okay, thanks for the introduction. Thanks for the invitation. Super happy to be here. Right, so I want to say something about, as Peng said, multiplicative vertex algebra is an equivariant K-theoretic wall crossing. So in order for me to say anything about this, I should first start off with something about equivariant K-theory. So what is equivariant K-theory and why should you care? And for the purposes of this talk, and also personally from my own perspective, I think of equivariant K-theory as some kind of refinement of equivariant cohomology. There's some abstract machine that says if you start off with some one-dimensional group, you can associate to it some generalized cohomology theory. And so if you start off with the additive group, you get ordinary cohomology. If you start off with the multiplicative group, you get equivariant. You get some version of K-theory. And of course, if you're very fancy, you can plug in some elliptic curve and you get some elliptic cohomology, which I'm not going to say anything about today. There's more than enough experts here to say something about that. So anyways, equivariant K-theory. So we have a space X and some group G acting on it. And for us, X will generally be some scheme, maybe later on some stack. And for the algebraic geometers here, we're going to assume it's quasi-projective. It's not really that important, but it's maybe psychologically important. And G will be some reductive group. Okay, so that's the setting. And then what is equivariant K-theory? It's some group Kg of X, which roughly speaking is you're going to take the set of G equivariant coherent sheaves on X. And if you take two coherent sheaves, of course, you can add them together. So this has some group operation. And you're going to mod by some relations which come from short exact sequences. So you have something like if you have a short exact sequence, F1 to F2 to F3 to 0, then you'll have a relation like F2 is going to be equal to F1 plus F3. Okay. So that's equivariant K-theory in a nutshell. And an alternate way to say this, of course, is that you're going to start from the entire derived category of all coherent sheaves, which are G equivariants, and you're going to pass to what's called the growth and decay group, which is usually called K0. So these are two equivalent ways of saying the same thing. And you might wonder, and this is an important technical point, why do we take coherent sheaves here? And the answer is, well, equally well, you can consider variants of this group that I've written down, where instead of taking coherent sheaves, you really just take vector bundles. But due to some small technicalities, you can take vector bundles. Or even better, you can start not from DP-Co, but from the full subcategory of all perfect complexes. These are things which are locally vector bundles. Curve Gx. And that will give you some variant of the K group. So this will give you something which I'll call Kg perf of X. Okay. So there's some variants you can do here. And I want to emphasize that Kg perf is kind of very, very, very different from Kg of X. Okay, so one notable difference is that if you have a vector bundle, you can always pull it back along any morphism. Whereas if you just take some coherent sheaf and you do some derived pullback, that might not stay coherent. So there are some important functoriality differences between the usual K group and this K group of all perfect complexes. All right. Maybe this is a good time to also say, so for example, the K group of all perfect complexes has some tensor products. It makes sense to take two perfect things and take their tensor products. Whereas again, if you take the tensor product inside DB code, that you run into issues in general. Okay, so this exists and makes into a KGX module. So if you take a perfect complex, you can take the tensor product with some coherent sheaf. That makes sense perfectly fine. Okay. Because here I said the word stack, I think right now it's important for me to say that thinking about equivariant sheaves on X is the same thing as thinking about ordinary sheaves on the associated stack X mod sheaf. So note, this is almost a tautological statement that thinking about ordinary sheaves on the stack X mod G is going to be the same as thinking about G equivariant sheaves on X. Okay. And if you're a stackily minded person, this is maybe one reason why you would care about equivariant K. Okay. Okay. So let me now try to compare and contrast this with equivariant cohomology, which I'm assuming more of you might be familiar with. Yeah. So far, it's just an abelian group. Oh, I mean that first of all. Yeah, I guess now that you pointed out, I can say something even stronger. Sorry. Sorry. That's absolutely right. Thank you. My bad. Okay. Right. So now let me try to compare and contrast this with equivariant cohomology. Maybe I'll just write the following. I don't think there's a canonical preference for either. If your space X is smooth, then every coherent sheaf will have some finite resolution by vector bundles, and so they'll be the same thing. If you're not smooth, it depends on what properties you want to get out of this. So later for us, and also the reason that I'm really emphasizing this whole distinction between coherent sheaves and vector bundles is because for us later, we're going to explicitly want to work with KG-perf for very specific reasons. One of which is that there are arbitrary pullbacks inside KG. Right. Yeah. So maybe on Friday I'll say something about that actually. Yeah. So the quotient of KGX by KG of perf is some important invariant of the singular locus of X. And this is like some categorification of critical cohomology. And on Friday, I'll say something about that. That's related to maybe what should be the second half of the abstract. Okay, so this group, KG of X, is richer than somehow like the naive sort of thing that you might want to write down if someone asked you to define what equivariant K theory is. Namely, maybe knowing equivariant cohomology, you'd be tempted to say, well, it should be the ordinary K theory of this construction due to Borel, where you take the classifying space, sorry, the universal bundle over the classifying space, and you take this associated X bundle. And if you replace this K here with H upper star, this is literally the definition of G equivariant cohomology. And so of course you can equally well think about this group. Okay. And I want to stress at this point that this version of equivariant K-theory is somehow not genuinely equivariant. Okay, so for example, I want you to keep the following picture in mind. So let's say G is C star. This is the simplest possible reductive group you can take that's non-trivial. And the picture you should have in mind is the following geometry, where instead of thinking about these as groups, you're going to spec everything. G point. And so I should say that not only will these things be groups, they will be modules for kg of a point, because any space maps to a point and you can pull back along that map. Okay. So you can think about the induced map on spec. And what's this going to look like? The underlying space will look like some C star. In fact, it'll be exactly this group G. And spec of kg of x will be something which sits on top of this C star. And this is in line with viewing K-theory as some kind of thing associated to the multiplicative group, because you can do the exact same thing with equivariant cohomology and elliptic cohomology. And in fact, I'll just draw those pictures really quickly here. You can ask yourself, what is spec of the C star equivariant cohomology of a point? And the answer is that there you'll get the Lie algebra of this C star. So you'll have some copy of C. And on top of it will sit spec equivariant cohomology. And everyone knows how to go from C to C star. This will be some kind of exponential map. On the base, it really is an exponential map. Okay. And equally well, you can imagine that equivariant elliptic cohomology will be something which lives over an elliptic curve, which will be this C star modulo the elliptic modulus, as some of us already saw in Andre's talk. And on top of it will live, oops, that's the wrong color. On top of it will live equivariant elliptic cohomology of x. This is equivariant elliptic cohomology of a point. Okay, anyways, so there is some kind of overarching picture like this. And what I want to emphasize is that there's a theorem due to Atiyah and Siegel that says actually this naively equivariant version of K-theory somehow only sees what's happening around a neighborhood of the identity inside C star. So there's a point in here 1, and there's some formal neighborhood around it. And a theorem by Atiyah Siegel says that actually, if you try to do the usual Borel construction here, you're going to get the actually equivariant K group, the thing up there, kg of x. But you'll only get its formal completion at the augmentation ideal. And the augmentation ideal here is just all rank 0 things inside kg of a point. Okay. So in particular, inside this picture which I've drawn here, we'll see later that there will be interesting things happening at non-trivial roots of unity of this C star, which in particular are not seen by this naively equivariant version of K-theory. And in fact, if you try to write down some kind of equivariant Chern character to compare equivariant K-theory with equivariant cohomology, that Chern character will factor through this neighborhood. Okay. So the moral of that story is genuinely equivariant K-theory really captures more information than what happens inside equivariant cohomology. Okay.
Make sure I understand. What is the I here? The I is this neighborhood of 1. What is I?
The I here is some ideal inside this ring, and it's the ideal consisting of all rank 0 things. So things of the form 1 minus some character of G. Yeah, it's just functions that vanish at 1. That's right. Yeah. It's the completion you would expect from this picture that I showed. Okay, so that's the short blurb on equivariant K-theory. Of course, there's a lot more interesting things that I could say, but in the interest of time, let's just leave it at that. Are there any questions? Okay, great. Let me now say something about this universal wall crossing business. So what is this? So first, let me attribute this to some people. Okay, so at some point last year, if you click on Dominic Joyce's name on the archive and you see what he's been posting, there's some gigantic 300-page preprint with the word universal wall crossing in its title. What I'm about to explain will be some enhancement of that, which will hopefully be less than 300 pages. Okay, so this is some stuff by Joyce. This is supposed to be a more modern formulation of some older stuff for Donaldson-Thomas theory and its wall crossings, which was done much earlier on by Joyce and Song. And what we'll achieve at the end of today, hopefully, is I'll explain how the material inside both of these works can be lifted up to equivariant K-theory. And we'll see that this lift is interesting not just for studying wall crossing, but also to take a lot of the structures which appear in Joyce and Joyce Song and to make them multiplicative. In particular, one of these structures is an ordinary vertex algebra, which we'll view as an additive construct. And we'll see how to use geometric methods to produce what's the correct version or the correct notion of an equivariant multiplicative vertex algebra. That's my little contribution. Okay, so what's the setup? Here you have the word universal, so you should imagine that the setup is somehow really general. So you're going to start off with a stack. So we're going to start from a stack M. And what's the stack going to be? The stack is going to be the moduli stack of objects in an abelian category A. Okay, so A here is some category which we'll take to be C linear, abelian. It's possible that there might need to be more words here. I don't really want to think in terms of something which is so general. So what we'll actually do is I'll say words, and you should keep in mind that A, for most intents and purposes, you can think of as the category of all coherent sheaves on some space X. Okay. Well, at some point I'll need some virtual classes. So I mean, you can do this in whatever generality you can construct virtual classes. Yeah, it's possible that a lot of the algebraic constructions, which I'll explain, work over not just an arbitrary field, but maybe even an arbitrary ring. But for actual wall crossing applications, we're really going to need to work over C. Anyways, so for all intents and purposes, we're going to pretend that this category is the category of all coherent sheaves on some space X. X is going to be some quasi-projective, maybe even variety. And for wall crossing purposes, we're going to think maybe like X, maybe the dimension of X is at most 3. Somehow, once you get into higher dimensions, it becomes harder to do the kind of intersection theory that we want to do for wall crossing. And we want to do all of our geometric constructions equivariantly with respect to some torr. Yeah. Oh, I'm sorry. Yeah, no problem. Sorry about that. Okay, let's switch to green. Is green okay? Yeah. So we're going to want to do everything equivariantly with respect to some torus T which let's say acts on X. So this is some algebraic torus. Yeah, so yeah, sure, you can pretend X is an AN surface if you want. So for a really explicit running example, you can pretend X is your favorite surface. It doesn't even have to be compact. You can take a toric threefold. That's right. Yeah. Yeah. So I'm about to say something. So you fix your category, which for us now will be some category of all coherent sheaves, and there will be some geometric moduli stack whose points correspond to the objects in this category. Okay. And points correspond to objects in this category. So it's like a moduli space. And the word stack here is just supposed to indicate that we're keeping track of the automorphisms of each object. So stack really means you record. Yeah. Yeah, that's right. Somehow that doesn't really come into play here. So the maybe more general answer is I believe a lot of the machinery which I'm about to explain really does work for when you relax the abelian condition on this category. You can really think about the full derived category whose moduli stack, I'm told, is some kind of infinity stack, because now the automorphisms are automorphisms up to homotopy, and so on. And so there, I believe it's kind of important that you take advantage of this extra structure in the automorphisms. But somehow I like to be more down to earth, and we'll think today about regular old stacks of abelian categories. Okay. Great question. Not sure. Yeah, I think on the A model side you have some derived category, and it's not so clear what the abelian.
Right, but he's actually doing.
Yeah, I really want this to be abelian.
Sorry. If you just look at stable objects, then this is going to be like, in other words, special account.
I don't know enough to comment.
So.
Okay, then you can think of that category, and we'll try to consider. I'm not sure. The A model is very mysterious to me. Okay. Right. So we have this moduli stack, and in general, this moduli stack will have many components indexed by something which we'll call alpha. For coherent sheaves, I mean, every coherent sheaf has some topological data associated to it. This is the Chern character, right? And so you'll have. That's true. Yeah. So if you want this alpha is the K-theory class of the coherent sheaves, which we're considering. Okay. And the action by this group T on the abelian category will induce an action on the stack. Okay, so T also acts. So the reason that we want this is because later we're gonna want to do some integrals, and to do these integrals over non-compact things, we're gonna need some kind of localization with respect to the group. So you can pick any group that you want, but at some point we'll need to run localization. I suppose so. Yeah. Oh, I don't think I had any more to say.
If we were to take the AN surface line,
sorry, which automorphism? The T or this?
So you're just recording the action of the torus.
Not derived.
And I'm recording the action of automorphism on the morphism of the category object.
Yeah, so in this category A, of course, you'll have some kind of data to do with the automorphisms, but the moduli stack itself, it doesn't really care about that stuff. I mean, it's just some space where each point corresponds to an object in here, and attached to the point is also the information of the automorphisms of that object. Yeah.
No, I think that the subcategory of stable objects, and it's their exact sequence makes sense.
Okay. Okay. So yeah, you're free to think about some other category if you. Yeah. Okay. So since we're talking about automorphisms, the first thing I want to point out is that every object in the category of coherent sheaves has at least one kind of automorphisms. If I hand you some sheaf, you can always scale it. Right? So every point in here has at least a C star stabilizer. And we want to get rid of that. So we're going to remove C star scaling. And part of the reason we want to do this is, in the end, we want to answer some kind of wall crossing problem about what happens when you change some notion of stability condition. And to answer questions like that, it's best if we get rid of as much of the automorphisms as possible. So down here, we're going to have a space which we're going to call MPL. And we'll have the same components. And roughly speaking, you can think of this MPL, or you can think of this map as some point mod C star bundle. Okay. So it has the exact same geometric points. It's just that the automorphism groups are now small. Okay, so as a very concrete example, if you take the moduli stack of vector bundles, which are d-dimensional vector spaces, this is going to be, there's only one d-dimensional vector space, but it has a GLD's worth of automorphisms. So that's some stack. And the PL version of the stack, that's the PL, is going to be where you take the stabilizer group GL and you mod by the things on the diagonal, main diagonal, and you're going to get PG. So that's, which is the stack of projective vector spaces. That's right. That's the reason for this notation PL here. You're supposed to think it's some projective linear. Okay. Great. And now we're going to introduce some stability conditions. Now we're going to introduce some stability conditions. And I don't want to be super, oops. I don't want to be super detailed about what kinds of stability conditions we're thinking of. You can just imagine slope stability or some kind of, yeah, just slope stability, I guess. You can also think E-cycle stability if you want. So inside here, yeah, so stability condition for me is some numerical function on the objects of this abelian category, which induces some numerical function on the stack. And yeah, you can stratify by the values of this numerical function. Yeah, Harden or something. Yeah, that's right. So I mean, you can think you take like slope stability, where you take the degree over rank or something. That's some numeric function for each sheet. Okay. And so, in lieu of explaining all that, I'll just draw some picture. Okay. So you've got MPL. Okay. And we're going to have some notion of stability such that the semi-stable locus. Okay, so inside here we'll sit the semi-stable locus. Let's fix a component alpha. So we'll fix the K-theory class of our sheaf. And we'll take the semi-stable locus with respect to some stability condition tau. Okay, so some stability. And we'll assume that the semi-stable locus is an open locus. Okay, so this red circle is almost the same as the white circle. Okay. And of course, inside the semi-stable locus will sit the stable locus. And this green inclusion can really be anything. Okay. It could even be that the stable stuff is empty. And the stable stuff has no automorphisms. And so you should think that it really is some kind of quasi-projective scheme. So there's no stackiness involved. Okay. So this is really a quasi-projective scheme. Okay. And the fundamental question in wall crossing is what happens to this green circle as you vary your notion of stability tau. Okay, so you have other loci in here, which will be M stable alpha with respect to tau prime. And the intersection of the green and the yellow stuff could be anything. It could be some complicated thing. And somehow we want to capture some information about how the geometry changes as we go from tau to tau prime. And the picture for wall crossing to keep in mind now is that then you have some space. So this is like a space of all tau, whatever that means. And inside the space will be some called walls, which partition the space off into some chambers. And then you should think that in some sense, the behavior of the stable loci as you vary tau is somehow constant-ish in each chamber and only really jump as you cross a wall. What happens when you cross a wall is that certain objects in your category will destabilize, certain objects will restabilize themselves. And so the geometry here really changes. Okay. These are some walls. Okay. All right. Yeah. It can really be anything. It could even be that these are empty. And right. It's what? I think when you're non-empty. Sure. Yeah, that's right. Yeah, but right. Exactly. Yeah. So yeah, I guess it's true that more can be said about these inclusions than what I've said, but I don't really need to use anything about that. Oh, I'm sorry. That's yeah, my bad. Okay. So what are we going to do? Step one, or step two, I suppose, is we're going to relate certain kinds of enumerative invariants on the green thing to the same enumerative invariants on the yellow thing. Okay, so we're going to relate this object called M semi-stable tau and M semi-stable alpha tau prime. Okay, so let me explain what I've just written. First of all, if you want to study how the stable loci change as you cross a wall, generally you're going to have to understand what happens exactly on the wall when your stability condition really lies on one of these walls. And there, you really pick up objects with extra automorphisms, really like strictly semi-stable objects, things which are in the semi-stable locus, but which are not in the stable locus. So the moral of the story is if you want to understand wall crossing for stable loci, you're kind of forced to also understand what happens for the semi-stable loci in general. And so the philosophy is that if that's forced upon you, you should just start with the entire semi-stable loci anyways. Okay. And for various tau, maybe for generic tau and alpha, it will turn out that there are no strictly semi-stables, and this really is the stable locus. But for special things, maybe this is something bigger. Okay. So associated to semi-stable loci, we want to have some classes, and these classes will live inside the homology group. Okay, so homology, not cohomology, maybe T equivariant. Actually, let me not say anything about equivariance for now. Of what? So for those of you who have some experience with enumerative geometry, these are going to be approximately something like virtual classes, virtual fundamental classes for say stable loci. But if you want to compare two classes like this that live in completely different loci, you're going to have to put them into some common parent or common ancestor or some common home where they can be compared. Right? Exactly, right. So the stupidest possible thing to do, which is actually not that stupid, is you're just going to push everything forward to the ambient stack. And that, exactly, that push forward is an open push forward. Right? And so you're not going to be able to do that kind of push forward in something like Chow or something like cohomology. Okay. There are some cohomology theories that have arbitrary push forward, and in this case, we're going to take homology of the ambient stack, MPL. Okay. So the homology of MPL is this common home that we're going to use to compare all of these invariants. Okay, but even before we try to relate these invariants, we're going to have to do step one, which is we have to define them. And you want to define these for all tau and all alpha, regardless of whether or not you have strictly semi-stable objects. Okay. I guess also all tau prime. Yeah, so right, so that's a good question. The answer is we're going to avoid considerations like that by doing something better than the naive kind of open push forward. So I'm about to say what these classes will be for us inside equivariant K theory, and there'll be something slightly better than the naive open push forward. Yeah. Okay, so let me first tell you what these classes are in the easier case. Okay, well, maybe even before I do that, I should ask, are there any questions about the setup or the question that we want to answer?
What do you mean? Refactor a stack?
Uh-huh.
A stack?
Uh-huh. Oh yeah, that's a good question. So maybe I should say everything that I'm explaining right now is from the original preprint of Joyce. And his approach toward thinking about the homology of a stack is you're going to take the stack, it has some kind of topological realization, like how point mod G can be realized as BG by just gluing some cells, right? And then you take the homology of that topological space.
Here, I don't lose any information because I come to
Yeah, so here you don't lose, well, I mean, here you still lose some information depending on.
But I thought there's some sort of better version of that experiment. So you shouldn't concentrate on this.
Yeah. So maybe let's not focus too much on this homology group. I want to give you a notion of K-homology, which works slightly better than this. Okay. But at least for Joyce and for people who work in homology, homology of a stack means you take topological realizations. Okay. Any other questions? This isn't erasing very well. What's a what? It's that will depend on what G is. So if G is C star, you'll get the homology of CP infinity, which looks like the cohomology, but it goes in the negative direction. So it's in that case, it really is the continuous dual of the cohomology of CP infinity. And I guess when G is like a Lie group or something, it'll be it'll be 4.1. Yeah, I think that's right. Something like that. Yeah, that's correct. Okay, let's move on from homology. Sorry. Okay, so A, if stable is equal to semi-stable, then what usually happens in this whole business is there's this construction of what's called the virtual fundamental class. This is some upgrade of the usual fundamental class to be more deformation invariant. There's a whole slew of reasons why you want to work with it. I don't really want to say too much about it. Okay, so if stable is equal to semi-stable, there is some object called MSST alpha tau associated to this locus, which really is a scheme. Okay? There's a thing called the virtual fundamental class, ver. And this can be pushed forward from the stable locus into the ambient thing to give you the invariance that we want. But that's not what I'm here to tell you about today. Alternatively, I think the following kind of construction should work much better, which is that instead of thinking about this virtual class, we're going to ask ourselves, what do we want to do with it in the end? And for all of these problems in enumerative geometry and algebraic geometry more generally, the only thing you're ever going to want to do with this is you're going to cap it with some cohomology class, and then you're going to integrate. So we'll just write something down which encapsulates exactly that. We'll write down a functional which eats. Okay, so this will eat something in something like the cohomology, or maybe even the Chow group. Okay, maybe even T equivariant on MPL. Something in its formal dual. So instead of thinking about the virtual class itself, we'll think about functions which eat some class on the ambient stack, pairs it with this virtual cycle. So restriction to the semi-stable locus, which here for us is just the stable locus, and then it will integrate over this virtual class. Sorry, maybe I should write this out. And so this kind of object is something which lives in some kind of formal dual of the Chow group, maybe equivariantly of the stack itself. Okay. C lives in Chow homology. Or even better, because we want to work in equivariant K theory today, we're going to write down the exact same kind of expression, but inside K theory, where you eat some sheaf E on the K theory of MPL, and you're going to write down the K theoretic analog of this expression. And in K theory, integration is replaced with Euler characteristic over the locus M stable tau. And you're going to take this E and you're going to pair it with the K theoretic analog of this virtual class, which is just called the virtual structure sheaf. And somehow, while the first line that I've written here for Chow homology is supposed to be kind of approximate, I want to be very precise about where these kinds of functions live. inside K theory. So these will live inside my notion of what's called equivariant operational K-homology. Okay, so it'll be KT written like this, ML, okay, and this is somehow the usual K-perf, but with the indices flipped. It's supposed to remind you that it's some kind of homological version of. No, there's no dual here.
We have both lower star and
I have both lower. Oh, I see. I'm sorry. Yes. Thank you. Does that make you happy? What's the what? Oh yeah, these are finite dimensional things. Yeah. So
But are there real things like we would actually know what these are, or somehow we'll learn how to operate with them?
for specific abelian categories, there you somehow say various explicit things about these loci, but in general, I mean, they're just some geometric spaces attached to the abelian category that we started with. Yeah. So
one day when this guy will be defined as some kind of derived scheme, we just say take derived, pull back, and
well, when that day comes, I'll have to learn that too. So
no, but that's supposed to be like some kind of, it's supposed to be some kind of derived structure sheet of each step.
that's right. I mean, in principle, this should be fully derived, and this really should be like the usual structure sheet of that derived thing. That technology, I think maybe exists, but hasn't really been written down in this kind of context. Anyways, I'm a little old-fashioned, so this is like an actual ordinary scheme with some ordinary virtual thing.
So virtual is subdividing on MPL.
O virtual will be the thing which is analogous to the virtual fundamental class of the semistable locus. So it's a sheaf which lives on the semistable locus. Or here is the stable locus.
Okay, so it depends on alpha.
It depends on alpha and tau. That's right. Yeah. But the E doesn't. The E is something on the ambient stack, which we're going to restrict to whatever open locus we care about, and then we're going to do this interface. Okay, so let me be more specific about what this K group is, because I think it's kind of interesting. Here's a small definition. So this is called equivariant operational K-homology, and I'll explain what this word operational means soon. And first, I should maybe say there's many notions of K-homology out there, and this, to the best of my ability, seems to be distinct from all of them, unfortunately. But if someone has seen something like what I'm about to explain, please let me know. I'd be very happy to see some precedent for what I'm writing. I'm absolutely sure I'm not the first one to have written something like this down. So what's this going to be? K perf T of some stack X is going to be a set of all collections of, let's give this a name, let's call it phi. What's phi going to be? Phi will be some collection of functionals from the actual K theory of perfect complexes. So note here that the perf is on top. This is like the actual K theory that I said at the very beginning, okay, of X relative to some base S. And these phis will be functions from this thing to K perf T of the base. So an element inside this K-homology is a collection of functionals, one for each possible base S. And S here can really be some arbitrary stack. And these collections have to satisfy some compatibility conditions. Okay, so plus axioms, e.g., okay, you have to have some compatibility that says if you want to apply phi S prime for some base S prime from K per T X S prime to K per T S prime, that should be compatible with applying phi with some other base S. This is some kind of neutrality in the base. And this is by some pullback along some map from S to S prime. So this is some kind of neutrality. Because we're working equivariantly and there's no general kind of equivariant localization principle for stacks, we're going to impose that by hand. We're going to say something like you want equivariant localization. So this is another axiom. And what's it going to look like? It's going to look roughly like the requirements that K per T X cross S. This is going to have to factor. So if we want to think about a particular functional in our collection, it should factor through something which resembles the T fixed locus of our stack X. Now the actual T fixed locus of a stack is kind of annoying. It can be much larger than you think. So we'll just say that it factors through some other stack F via pullback. Where the action of T on F is trivial. So if you think about what equivariant localization says, it's exactly some statement like this. Okay, that some integral that you want to compute on your whole space X actually factors through some other function on some other space which is fixed under your T action or Tx trivial. Okay? So you have some kind of localization axiom like this. And then we have a kind of annoying technical condition, which I would be very happy if someone could get rid of for me. So maybe let me write it down here. Then we're going to impose some technical condition. So that's e.g. what's called a finiteness condition, which says roughly something along the lines of, if you now take this function on the fixed locus. Okay. No, so the yeah. So you can assume the nicest things you want about X. It can be smooth. It can be a smooth variety even, right? And we're going to be thinking about phi S here will be functionals like this. It'll be things which eat something on X, restrict to some stable locus, and then pair. So this statement really is like usual equivariant localization where there are denominators, but after you add them all up, it lands in the non-localized thing, assuming some properness. Which little guy? This one? This one. Yeah, that's because the denominators aren't in here; they're in this map. Yeah. But I mean, of course, you can add a.
There's some kind of map.
Right. Yeah. So I mean, if you want, psychologically, you can add a subscript localized here, and I think that will certainly answer your question. But even more strongly, it's just not necessary. Yeah, so if we were working with the actual virtual class, of course, then here we would need some localization. But here, the denominators that you're thinking of appear in this map, I think. Okay. So then we're going to have some finiteness condition, which says roughly that at this map from the fixed part, when you apply it, so you can feel free to zone out here. This is like some stupid technical thing. If you apply it to some high enough power of the augmentation ideal, so again, what is this? This is rank 0 things inside the non-equivariant K group perf of F cross S, which of course sits inside the equivariant K group of F cross S. If you apply to some high enough power of this augmentation ideal, this should sit inside the augmentation ideal of the base, maybe also to the same high enough power, maybe up to some constants. And this kind of condition is automatically satisfied if F is a skew, basically by virtue of the fact that this augmentation ideal is nilpotent. If you take anything in here and raise it to a high enough power, this whole thing is just going to be 0. And if you apply a function to 0, you get 0. So this will be true. But for stacks, you really have to impose this by hand because it's not true anymore. And we'll see later that this really is very important for the vertex algebra. But somehow this condition is what makes it annoying to work with these groups. And it'd be nice to have some kind of cleaner reformulation of this. Anyways, okay, so let me not spend too much time on that. Okay. So the original X, right? So let's see if I still have it on here. So we do want these virtual classes, and it's hard to construct these virtual classes when you're thinking about coherent sheaves on something of really high dimension. And part of the reason is that the input to the construction of these things is some kind of tangent obstruction theory. So you have some naive tangent space and you have some obstructions to these deformations, but you're not allowed to have more. You can't have obstructions to your obstructions. If you do have that, we don't know how to construct these things except in very special cases. So when you're in dimension 3 or less, it's usually very easy to make these extra obstructions to obstructions just vanish for purely dimensional reasons.
And X is a homework, what one word?
X can just be some complex
Well,
algebra.
I like to still talk about the hard math. I think those are the setting for if you want to understand what it's building condition of any sort. These are the ideal places first. So it's a point to
Right. I mean, the what I'm saying can be extended to 3-folds and for some very special 4-folds as well. But I think if you go higher, there's no systematic construction of these things. So you can imagine for the category of coherent sheaves, the deformation theory of a sheaf is basically controlled by its self-X groups, right? So X of the sheaf with itself. And these X groups can really go up until whatever the dimension of your space is, right? But to construct these virtual cycles, you really want X3 and above to just vanish.
That's somehow relative to the function constructor.
That's
Suppose we had some kind of conditional scheme, right?
Yeah, so if you want to derive everything, then I think what I'm saying is not an issue. Yeah,
No,
so
you don't need to, if you just have this actual D3 version of this whole verb, you just have that.
you would be happy with that for what I'm writing down, but you would be maybe unhappy with the connection of that with any kind of enumerative problem, right? I mean,
No, I think it's fine. Definition is just the same. To have that.
no, I just mean that like you have some space and maybe you want to count like actual curves in it, right? And so then it's maybe not so clear if you just ignore the condition that you vanish.
Well, for example, I'm saying something. Suppose you want, kind of, you tell them information, you subtract the abstraction, you want to put the abstraction to abstraction. So imagine there was a way to do it. There was some actual shape of the algebras in your space. So that it's K theory class was that shape you want to construct. And if that is like some kind of complex between shapes, you could just.
Yeah, sure. That's okay. Yeah. That will be fun. I just don't know how that will play with, I suppose, what I'll say in the next half hour or so. Yeah, that's certainly some definition you can make, formally speaking.
I don't think that definition exists.
Right. Yeah. I agree.
I will be aware of it.
Okay. So we have some notion of K-homology, which roughly looks like these kinds of collections of things. And here is where it's kind of crucial that we took K-theory of perfect complexes, where you have arbitrary pullbacks. Because in the dual thing, so this is some kind of dual version, you get arbitrary push forwards. And so in particular, you can then push forward along this thing which I just erased from the semi-stable locus into the ambient stat. So those kinds of push forwards always exist inside this notion of K-homology.
And then the X is like smooth compound, and it's somehow this coincide with some other notion of K-homology.
Yeah, that's a good question. I haven't really been able to pin that down because of this annoying finiteness axiom. So if you remove this finiteness axiom and you just keep the localization and maybe that kind of naturality, then yeah, I would believe what you're saying, where this is really like some continuous dual of maybe the usual K theory of perfect complexes on X. With this, I don't really know. This is like some actual non-trivial condition. Maybe I should say, Oh, here I just mean some function which grows linearly with respect to n. So I mean, maybe here you have to put like 2n or something, or maybe n minus 3, I don't know, but it should be linear with respect to n. Maybe this is a good time to say, for stacks of the form point mod g, you can really just see what this finiteness condition means, and you can really match this up with the usual topological notion of what K-homology of the topological realization is. So in some sense, this finiteness condition is kind of removing what happens away from 1 in the very first picture I drew for equivariant K theory. Anyways, yeah, I don't know what these groups are for general stacks X, and it would be interesting to compute them.
So you say X is point mod G?
If X is point mod G, you get something which is identifiable with the topological K-homology of the topological realization of point mod G. Topological K-homology is it's some. Yeah, but that's like some super abstract description. Yeah, maybe in practice it's like the continuous dual of usual K theory. Somehow I like to avoid giving super abstract definitions like that. Okay. Anyways. Okay. So let me give you an example of what this finiteness condition is really doing for us.
Actually, I mean, you only want it, so to speak, at 1, and then there's a
No, you do. But somehow the imposed kind of vanishing. Yeah. So how about I write down what I was about to write down? And I think it will clear up your question. So finiteness means we want to impose it in effect to get something like this, where if you apply t fixed component of your map. And let's just work over a point for simplicity. Okay, so we have some trivial base. At some point or another, you're going to want to run equivariant localization arguments, and you're going to plug into here something like the kinds of contributions you get from localization, things of the form 1 over 1 minus some weight times some non-equivariant line limit. So z here is some c star weight. L here is something inside the non-equivariant K theory, maybe perf of the fixed thing. Okay. And so what's this going to be? Usually when you run equivariant localization, it means you just take this series and you expand it around z is equal to 1, and you get some huge infinite series. Okay. So we'll do that. We can write down the expansion around z is equal to 1. We get something like this. Over here, we're going to get our functional phi t point applied to 1 minus L to the nth tensor power. And what happens when you do equivariant localization on schemes is that for a sufficiently high enough power, these terms are just all going to be 0. The operator 1 minus L is nilpotent. But that is not true for a stack. Okay, so if this f is stacky and we had no finiteness at all, this really is an infinite series. And so what the finiteness axiom is effectively doing for us is it says, okay, well, if we don't truncate here, we can just forcibly say that this thing truncates after we apply this functional. So finiteness means that this actually is a finite sum. And this will be very important later on because our vertex algebras will be meromorphic functions. It'll have some meromorphic dependence on 1 minus z. And somehow you only want finite order poles. You don't want some infinitely singular things. So we really need to cut these off at some finitely negative points. And the only way that I know of doing that is to impose it as one of the axioms in this version of K-homology that we're thinking. This is certainly not automatic, even for things like point mod C star. Okay, so that's what.
Why do you don't want infinite sum?
Yeah, so partially because inside, generally when you do K theory, you only think about finite sums of things. Otherwise, you have some infinite sum, you might get something infinite rank, and that's not really coherent anymore. But also because, like I said, at some point, this will be part of the geometric inputs to a construction of vertex algebras. And vertex algebras are kind of like meromorphic objects in Z. And so in particular, their poles in Z will have finite order. So you don't want like some kind of essential singularity or something. You want some finite order singularity. Okay. All right. Which one? Mm-hmm. That's right. That's right. So I'm about to say something about that. Yeah. So that's to be seen. Yeah. There will be some vertex algebra on M which will descend to M. Okay. All right. So I've spent a lot of time saying what happens when stable is equal to semi-stable. But now at least we know the kinds of objects that we want to think about, and we know sort of the home that they live in. Okay. And you know, if you zoned out during that, that's totally fine. But now it's time to zone back in because I'm about to tell you what happens when the semi-stable locus is strictly bigger than the stable locus. And this is where the interesting wall crossing stuff happens. Okay. So let me push this up. Okay. All right, so B, if semi-stable is not equal to stable, then we actually have to do something non-trivial. And how this went originally in Joyce's song, and how it also went in Joyce, and how it will keep on going probably until the end of time, is you're going to construct some kind of auxiliary stack, some auxiliary M, we'll call M pairs. And it will be indexed also by alpha and by an additional integer k. And we're going to think that k is some pretty big integer. And what is this? This is going to be the moduli stack for the following kind of thing. It will parameterize some vector space V, which for us will be one-dimensional. So V is isomorphic to C. But which isomorphism, that's up to you to pick. Okay, so that's part of the stabilizer. And V here will act as some kind of framing for our sheaf. So V really rigidifies the sheaf. V will map via some section S, which is also part of the data, into global sections of your sheaf twisted up by K. Okay? And that's part of why we want K to be really big. So E is here, and this E is some point in the original. It doesn't really erase well. E is some point inside the original moduli stack that we wanted to think about. Okay, so this is some auxiliary stack consisting of essentially our sheaves, but with some framing. And what the framing does for us is it removes extra automorphisms. So on here, there's some way to lift a stability condition on M to some stability condition on M pairs. And that lift will have semi-stable objects always just stable. So on this pair stack, you don't have this issue where you have strictly semi-stable objects. This is true always. Okay. And so what we'll do is in the end, we want to construct invariants for semi-stable loci of M. We'll construct them by some upper triangular transformation of known invariants on here. Because if semi-stable is equal to stable, we're back to the first case. And I explained how to do invariants in that case. Okay? So what we'll have is we'll have some formula. So the way to define semi-stable invariants in general is we're going to start from, oh no, I erased it already. I wanted to give a name to these invariants. So earlier we had some invariants that eat some sheaf and spit out the integral over the semi-stable locus of that sheaf. Right? Something like this. Let's give this a name. Let's call this Z alpha tau. Okay. So this is some universal enumerative invariant inside K-homology, inside our notion of K-homology. Okay. And what we'll do is we'll take Z pairs, we'll take this object for the pair stack, and we'll use it to define the semi-stable invariants that we want. So we're assuming that our stable locus is quasi-projective. So you have some notion of O of 1, you twist up high. Okay. Right. So we're going to do the following. We're going to say that we already know how to define these objects Z on the pair stack. And the pair stack admits a map, the forgetful map, to the original stack M alpha. Okay. So of course we can take this thing and push it down via this map. Okay. Let's call this map. And we're going to cap by some stuff. I don't really want to say exactly what the stuff is. It basically removes the contribution from the relative tangent bundle of pi. And this is going to be equal to a sum over positive integers n and alpha 1 up to alpha n adding up to alpha, such that the slopes in some sense of all these alpha I are equal. And you should think of this as, there's some invariant upstairs, and it receives contributions from all the things lying on the same kind of slope as the class alpha that you care about. And the contributions will be from these semi-stable invariants that we want to define. So we'll have some expression here involving the things we want to define. So Z alpha tau. So these are things we want to define. You should think of them as roughly equal to the functionals, roughly equal to these kinds of functionals, even if you don't have this virtual structure sheaf on the semi-stable vertex. And so it'll be Z alpha 1 tau, Z alpha 2 tau, up to maybe you have Z alpha n tau. And you'll have some scalar factor here, which has to do with Euler characteristic of alpha 1 twisted up by k. And so there's many things to explain about this formula. Let me first start with what these square brackets are. Okay. So this whole formula is happening inside the K-homology of MPL. And the non-trivial claim is that there exists a Lie bracket on the K-homology of MPL. Okay, and that's this Lie bracket. Secondly, this equation is not a proposition, it's an actual definition. Okay, so we use this formula to define these objects Z alpha I. Okay. And we can do this because in terms of these alphas, if you sort them by how much they decompose, this is some upper triangular transformation from the left-hand side to these objects Z alpha tau. Okay? And we know everything on the left-hand side. Okay? So you can use this to inductively construct what these Z alpha taus are. Right? But there's something funny going on here, which is that the left-hand side depends on this k. Whereas the right-hand side, the only dependence on k will enter in this scalar factor here. And so there's already some non-trivial claim being made here, which is that if you write down this kind of definition, the classes that you end up writing here, Z alpha tau, are actually independent of k. So that's already some non-trivial wall crossing statement, which is part of the definition of these classes. Okay, so these are all independent of k. Oh, I just mean that you take any sheaf in this class alpha 1, you twist it up by k, and you take Euler characteristic. I mean, this kind of Euler characteristic will be constant amongst all such sheaves. So. No, because you can rename, but you have to take at least one of them. No. So this is the definition of these objects that appear on the right-hand side. Yeah. We know everything about the left-hand side. These, yeah. So on this pair stack, the point of this pair stack is we've rigidified the original moduli problem. So originally, we don't know how to handle the case where we have strictly semi-stables because they have a lot of automorphisms. Yeah, there's no there will be wall crossing on the left-hand side, but even before we talk about wall crossing, we should first write down what we mean by semi-stable invariants that we use the wall cross in the first place. Right? So here we're writing down the definition of the objects we want to consider. And then after we do that, then the problem becomes how do these change as we vary tau. Okay, so I've made some non-trivial claim here that these classes are independent of K. Let me explain where this claim comes from. And in the process, we'll see where this Lie bracket and where the vertex algebra comes from. Okay. Okay, so what's the idea? The idea is the same as literally every wall crossing argument under the sun, which is that, so this is like every wall crossing works like this. The idea is to form some even bigger space, which is generally called a master space. Okay, so form what's called M master, which will depend on K1, K2, and alpha. And the idea is that this K master is supposed to interpolate in between pairs for K1 and pairs for K2. And the way we do that is we'll have some H naught E K1 up here, and we'll have some H naught E K2 down here. And we'll write down the usual kinds of pairs. V1 may be going into here, V2 may be going into here. And then we're going to have some kind of interpolation, V3, that maps simultaneously to V1 and V2. So we'll think about the moduli stack of these kinds of things. And on this moduli stack, you have a C star action, which scales, let's say, this map. Okay? And you can ask yourself, what is the fixed locus for this C star action? And the answer is the fixed locus will look something like pair stack for K1. That's one component. There will be some other component that's like pair stack for K2. And then you'll get yet a third component that has to do with some kind of interaction of K1 and K2. And that third component is really the thing which controls the discrepancy between pairs for K1 and pairs for K2. C star is going to act on this map. Yeah. So there's some map here. It's a map from a one-dimensional vector space to some other one-dimensional vector space, and it'll be scaled by the C star action. Yeah. Okay. And so what will happen is that when you run localization using this C star on this space, you're going to get something like this. So this is C star localization. You're going to get some statement that says Z master. So again, this is the thing we understand. Because on here, again, stable is equal to semi-stable. So Z master K1, K2 alpha, tau, maybe capped with some stuff. Localization will say this is equal to some contribution from pairs for K1. So Z pairs K1 alpha tau. And then there will be some kind of denominator from localization, which will look something like 1 minus ZL. So the weight of this C star is, we'll call Z. And then you'll have another term, which is Z pairs K2 alpha tau. Then you'll have some other denominator, Z inverse L prime, something like this. And then you're going to get a whole bunch of terms which come from loci where this E splits as a sum, E1 plus E2. So you'll have a sum over alpha 1 plus alpha 2 is equal to alpha of some stuff. Okay. So roughly that's how localization looks on this stack. And so now after boring everyone for an hour and a half, I could finally state the main theorem. which is the following. Theorem due originally to Joyce in homology and to me inside this K-homology setup is that this thing, this two stars, these cross terms, is of the following form. It's equal to y, and I'll say what y is in a second, of some class like z k1 alpha 1 pairs tilde z z k2 alpha 2 tilde pairs. Okay, so it's some contribution from K1 pairs and K2 pairs with some small modification. Okay, so roughly speaking, these tildes, this is Z pairs pushed to M, okay, not MPL. So this is some kind of expression which eats two objects living on M, and it will spit out something. So where, what is this operation y? This y is some operation which eats a thing inside K-homology of M alpha 1. And it eats another thing inside K-homology of M alpha 2. And it's going to spit out for you something inside the K-homology of M alpha 1 plus alpha 2, meromorphic in 1 minus Z. But there's some equivariance, so I'll write a subscript T here. I'll say a little more about what this means in 1 second. Okay, but for now, you can think of it as meromorphic series in 1 minus Z. And in fact, you can even explicitly just write down what this y is. You can really just ask, what's the formula? And the answer is the formula looks something like this. So y is going to eat something called phi, eat another thing called psi. And it will produce for you something in K-homology, which is a functional. So the functional will eat something. It'll eat a sheaf. Okay. And I have to tell you what this is. And the answer is, this is the thing where you start from the sheaf. You take the sum map, pull back of this sheaf. Okay, so for all these abelian categories, you can always take two objects in your category and add them. Right? So that's some map on the category, which induces a map on the stack, and you're allowed to pull back with respect to that map. Then you take Z, you record the degree in the first factor. Okay, this is some nonsense. And then you take the tensor product with some complex, which is a function of Z. And you can even make this complex very explicit if you want. And then to this whole thing, you're going to apply the external tensor C. Okay, so anyways, all technicalities aside, there's some explicit formula for what this operation is. Okay. And then the non-trivial. Yeah, I mean, you start from the sheaf on your ambient stack, you do some stuff. This is like pull back to the locus where your sheaf splits. And this is some explicit bundle. And the point is, after you do all this, you're going to apply your functionals phi and psi. It's just some formula. But the miracle here is that this formula defines for you a vertex algebra structure. So that's the non-trivial part of this theorem. Somehow, like if you just want to run localization, you'll get some formula like this. But what's interesting is that under suitable assumptions, on M, is y. Okay, so the following package of data forms some kind of vertex algebra. So it'll be a vertex algebra structure on the K-homology of the moduli stat M. The vertex algebra will have some notion of the vacuum state. So it will have some kind of translation operator D of Z. And then you'll have the actual non-trivial information of a vertex algebra, which is how the state field correspondence works. And the claim is that this formula is that state field correspondence. This is what's called an equivariant, multiplicative vertex algebra. So maybe let me say something about what these ingredients are. The vacuum state is basically the generator of the K-homology of M0. Okay, so usually for all of our abelian categories, the components for the abelian category of coherent sheaves, if the K class of your sheaf is 0, then you really just have the trivial sheaf. So usually these K homologies only have one generator. That generator is called the vacuum. This is the point. If it's not true for the category that you're thinking, we impose that as part of the axioms. And this translation operator is the operator Z to the degree. And DZ, this is the translation operator. So I haven't actually explained what an equivariant multiplicative vertex algebra is. Yeah, that I'll do in 1 second. But part of the data is some translation operator. And that's this DZ. It also has some geometric incarnation. Okay? And so the non-trivial part of this theorem is you get some geometric construction of some sort of vertex algebra from the wall crossing formula. And so finally, what will you want to do with this kind of localization? That's 0, 0, 0.
It's like 0 rank.
0 rank, 0 everything. Yeah, yeah. Sorry, I should have really emphasized that. Yeah. It's not the structure sheet. Yeah. Yeah, that's right. Okay. So what was the point of writing down this kind of localization statement? It's that in the end, you want to relate Z pairs for K1 with Z pairs for K2. And the way you get some relation is you take this kind of statement from localization and you take certain kinds of residues in Z. The left-hand side is some proper class, so it has 0 residue in Z. And the right-hand side will be something which looks like Z pairs K1 plus Z pairs K2 plus some cross terms. And so this vertex operation Y, after you take appropriate residues in Z, is going to become some Lie bracket. And that really follows from some general theory of vertex algebras, which I want to explain now. Okay, so as far as wall crossing goes, I don't want to say too much more about it, other than there's some geometric way to relate Z pairs K1 and Z pairs K2, and that relation is controlled by something coming from a vertex algebra, which will be some Lie bracket. And that Lie bracket is this Lie bracket from the formula earlier. Sorry, maybe that was a little technical. Let me maybe wrap up by just saying something general about how you should think about an equivariant multiplicative vertex algebra, and hopefully that will be of sufficient general interest to wake everyone up. Okay, so I'm going to explain this object now. And I'll explain it by analogy with ordinary vertex algebras. What's an ordinary vertex algebra? This is the data of some state space V, which in general you can take to be some Z module. It really doesn't have to be a vector space. And inside the state space will be some distinguished vector, which is called the vacuum. So this is this state, which I'll write as ket0 inside V. What else is there? There's some translation operator, which is some operator D of Z. Let me not write Z. Let's call it D of U. And in the ordinary setting, what it does is it takes a state and it translates. It maps it to some other state as some meromorphic series in U. And then you have the state field correspondence. Which is this Y. It eats two states in V tensor V, spits out a third state, again, as some meromorphic series in U. Okay. So these are usually required to satisfy some axioms. And I think there's many, many ways to write sets of axioms for vertex algebras. But regardless of how you write these axioms, they all look like the following shape. Okay, so for example, you're going to have something which resembles this thing called the locality axiom, which says that if you take a state C and you hit it with Y of BU, so B here is, so you fix some states A, B, and C inside V, Y of A, U, and you compare this with hitting C with Y of, sorry, one of these should be a V. One of these A, U, Y of B, U. And these should be equal for some notion of equals. So let me say that for, you can think of a vertex algebra as some kind of algebra whose multiplication has meromorphic dependence on U, on some formal variable U, in which case this kind of locality axiom is kind of like commutativity of your operators of multiplication. Okay? So what does this equality really mean? Here you have to be a little careful that where the left and right hand sides live. So the left hand side lives in series in V, valued in series in U, and the right hand side lives in series in U, valued in series in V. And these are two completely different modules. And to meaningfully compare them, this equivalence sign means that they're equal as expansions of rational functions of something in some sense the intersection of these two rings, which will look something like V power series in U and V, and then you'll have some meromorphic terms which are polynomial in U inverse, V inverse, and 1 over U minus V. So it's not true that the left and right hand sides are equal on the nose as series, but they are equal as rational functions in 1 over U minus V. That's the point. Okay? So I think regardless of how you write the axioms, you get some notion like this. All right. And so in particular, the only poles joint in U and V are going to be at exactly along the diagonal where U is equal to V. Okay? Or phrased slightly differently, the poles are at U minus V is equal to 0. So now let's try to make everything up here multiplicative in the sense that we're going to view these formal variables U and V as some formal variables on C, and we're going to apply the exponentials of it. Okay? So we're going to replace U with like e to the U. We're going to replace V with e to the V, and we'll get something. So if you want to make this whole thing multiplicative,
So the state field response is you take two operators, separate and separate, multiply them together and look far away, see what you get. The state field.
No. So you should think that the output of y being applied to some state A will be some kind of operator which has some meromorphic dependence on your formal variable u. So you can view, it's just some coordinate on the complex plane, and you have some operator which in some sense sits at u, and it'll move around. And what happens here when you ask what is y of AU, y of BV, it's kind of like asking what happens if you have an operator at u and an operator at v and you move them close together, and u and v become really close.
So when you order this, like you on the left of the equal sign, V is much smaller than.
It's
Yeah, that's one way to think about it.
that is one way to say it. Here I've written the algebraic incarnation of that. Yeah, so I mean, you can equally write it out in some kind of analytic terms, in which case on the left-hand side, u is much smaller than v, and on the right-hand side, v is smaller than v, or maybe vice versa. Something like that. Okay. So we're going to take our additive variables u, and we're going to replace them with multiplicative variables z, which are going to be roughly e to the u. Okay. And not only are we going to do this replacement, we're now going to permit poles. Okay, so a priori, u has poles at 0, which means z has poles at 1. But not only are we going to permit poles at 1, we're going to permit poles at arbitrary roots of unity. And this really goes back to what I said at the very beginning of the talk, where usually if you want to move from something additive to something multiplicative, the exponential is only going to show you what happens around some formal neighborhood of the identity. And from the algebraic perspective, you really have to allow some non-trivial stuff to happen elsewhere as well. Okay, so we're going to do this kind of replacement, plus we allow poles in 1 minus z to the k, where k is any non-zero integer. Okay. And so concretely what this means is that this vertex operation y of a z p is going to land you inside your state space, but now meromorphically in things like 1 minus z to the k. And maybe you have multiple poles and multiple kinds of roots of unity. Maybe you have 1 minus z k1, 1 minus z k2, and so on. 1 minus z kn. Okay. So now you have some phenomena like this. And now on top of this, you can choose to add in equivariance with respect to some torus. And what that will mean is that viewing this z as maybe some weight of some C star action, equivariance means that you're also allowed to add things like t, ti z to the ki, where ti is a weight of your equivariant group T. So now what's going to happen is your state field correspondence is going to give you something which is possibly has poles scattered all around the torus T, possibly with some multiple cover behavior in set. And that's genuinely something new in the equivariant multiplicative case, which you don't see in the usual additive setting. And this feature comes kind of at a cost. And the cost has to do with this word expansion up here. What did the word expansion mean? It meant that you took some function 1 over u minus v, and you did a series expansion, which is holomorphic in either u or holomorphic in v. Right? And that notion of how to do that series expansion is unique. This is no longer the case when you add in equivariance. So expansions in this kind of equivariant setting are now kind of ambiguous in the sense that if I hand you some function like 1 over 1 minus, let's say, t z over w, this is the equivariant multiplicative version of 1 over u minus v. You can somehow redistribute this t amongst the z and the w in basically whatever way you want, right? This can be expanded to live inside series 1 minus S1Z, 1 minus S2W for any S1 and S2 such that their product is equal to T. Right? This is like some stupid algebraic observation. And this is really something unavoidable in the equivariant setting, which you have to work around. So often what happens in the usual theory of vertex algebras is you say, okay, I obtain some identity from expansion, and I know exactly what this identity looks like because the expansion is unique. Here you can only say I get some identity from expansion and I have no idea what it looks like. It just has poles in certain places. And that's something you have to work around. In particular, okay, so in particular, this means you're going to have to modify the following kind of construction. So there's a proposition which really dates back to the very beginning of vertex algebras, due to Borchardt's, which says that, so for ordinary case, which says that if you take the vertex operation, y, a, u, b, and you take residue at u is equal to 0 to u, this is a Lie bracket. At this operation, a, b, this is a Lie bracket. And the way you prove something like this really is that you don't have many things to work with. You just have to use the vertex algebra axioms, and you use the fact that at some point, whenever you have these kinds of expansions, you know exactly what the expansions are. Therefore, you can take residues of those formulas. Therefore, you produce like things like the Jacobi identity. If you want to write down the same thing for these equivariant multiplicative things, so now this is the equivariant multiplicative case, you're going to have to change your notion of residue. And that's not just because everything is multiplicative now, it's also because you have no idea where the poles are. They can really sit anywhere on your torus T. So your notion of residue must be insensitive to specifically where these poles are. And somehow, one of the only ways to write down something that's insensitive to the precise location of poles while recording all the poles is to just sum over all of them. So in the equivariant multiplicative case, what you do is you take the residue of this same kind of expression. I can say it in an even cleaner way, which is that you take the residue at z is equal to 0 plus the residue at z is equal to infinity, which by the residue theorem is the same thing as adding up all the poles in between of the same kind of expression here, z dz. This is also a Lie bracket. And in fact, these kinds of residue maps, these things are called residue maps. And there is a notion of like the residue map associated to some kind of C-star equivariant cohomology theory. I think this is originally due to Metzler or something. And in fact, you can show that this is the unique residue map associated for equivariant K theory. Okay. This is some notion due to Metzler. Okay. And so I want to maybe end end on the following observation, which I think maybe some small subset of people here will find interesting, which is that in general, using this, I don't know if the formula is still up here, but at some point, I wrote down some formula for this vertex operation. It's some geometric formula, and it's a little hard to compute. Okay? It's a little hard to work with, and it's even harder to work with once you start asking what are the residues in Z in that formula. Okay? Because Z is some equivariant weight, and who knows what has what weight in Z. But there is a very special situation in which this Lie bracket is very much computable, even if you know nothing about what the vertex algebra is. And that very special situation corresponds in enumerative geometry to Donaldson-Thomas theory. The idea is to make the very elementary observation algebraically that residue map. So for example, if I give you a function f, which is some rational function, and it looks like some a hat genus. So it has some like thing down here like z1/2 minus z-1/2 maybe, and then up here you have something which is dual to this, some tz1/2 minus tz-1/2. Right? So these kinds of expressions really come from a hat genus of some self-dual sheaf, like E minus T times E dual or something. Okay. Then it's very easy to compute what this residue map is, because if the limits as Z goes to 0 and Z goes to infinity both exist, then that residue map really just is like the residue Z goes to infinity plus residue of f z dz. This is really just equal to the limit as Z goes to 0 minus the limit as Z goes to infinity of this expression. Sorry, yes, you're right. Sorry, my bad, yeah. There's nothing special happening with the residue. It's really just the multiplicative analog of du. That was a typo, apologies. And for these kinds of balanced rational functions, these kinds of limits always exist. You'll get something like t1/2 minus t-1/2. So when you try to apply this whole machine to enumerative theories where the obstruction theory really is of the form some sheaf minus the dual of that sheaf, then even if you don't know much about the actual vertex operator, or even if you can't identify the actual vertex algebra, the Lie bracket is very simple to compute. And the computation really comes from something like this. So
is there a way to somehow summarize what the answer is?
Yeah, the answer kind of looks like this. It's kind of like yeah, essentially it's like if you want to take the bracket of what I called Z alpha tau earlier with Z beta tau, it's basically equal to like some quantum number in chi of alpha beta. And the quantum parameter is this equivariant parameter T of Z alpha plus beta tau. So it's really like the usual quantum torus. But you have to be a little careful here, because it turns out this is only true for the functionals that I'm thinking of when you apply them to the structure sheaf. Sorry. You have to apply this side to the structure sheaf, and over here you have to apply this to the structure sheaf. If you apply it to something else, pull back along direct sum will create for you extra factors of Z, which will destroy this kind of self-duality. But even in the case where you take some functionals, like you integrate the structure sheaf over your space, I mean, these are already interesting enumerative invariants, which many people like to study inside equivariant K theory. In particular, you can find these kinds of formulas inside things like refined Vafa-Witten theory and some other forms of inside refined Vafa-Witten theory. So that's like if you do Donaldson-Thomas theory for local surfaces. And you get formulas like this, which were previously conjectured by Richard Thomas as some kind of K-theoretic analog of what's in Joyce and Song. But now we can actually prove things like this using the control that we get over these kinds of Lie brackets coming from the vertex algebra. Okay, so I'm sorry, I probably put everyone to sleep, but that's basically all I wanted to say. Yeah. Thank you for your 2 hours and 5 minutes worth of attention. This is a lot of attention.
Until this very last moment, where did you actually
Yeah, so I skipped a few things. At some point, I wrote down some formula for this vertex operation y.
Yeah,
and as part of that formula, yeah. So yeah, that's right. But right. But as part of that formula, you have a term which comes roughly speaking from something like the virtual normal bundle of something like m alpha plus beta. M alpha cross m beta inside m alpha plus beta. Yeah. And this is sensitive to what the deformation theory of M looks like. So in fact, this is kind of like the key ingredient. That's right. So at some point, I think I mentioned that in order to actually get a vertex algebra, it's not like you can plug in any kind of abelian category. You need some assumptions on either your abelian category or on its moduli stack. And one of the assumptions is that like these cross terms in its deformation theory kind of look like bilinear things. So for coherent sheaves, you have like x of EE. These kinds of cross terms look like x of EF, and they're bilinear in E and F. And you really need this kind of bilinearity if you want to actually, out of the wall crossing business, to actually get some vertex algebra. So in particular, you're not going to be able to apply this to like stable maps or something.
Let's say, no, the first problem is very in this situation, this situation, there's this other vertex algebra.
Mm-hmm. Yeah, that's right.
And then you just feel that stuff as an operator.
Right. So yeah, that's a good question. I'll talk about that on Friday. So that stuff is going to be some structure on the cohomology side of things, whereas everything that I've said here is on homology in some sense. Right? So I mean, of course, you can replace cohomology and homology with equivariant K theory and our notion of equivariant homology. And so I've written down some vertex algebra structure on the homological side. There's some other structure, maybe like a Hall algebra or something, on the cohomological side, and there's some compatibility theorem between these two. Precisely what this means for your vertex operator, I don't know, but presumably your vertex operator has some expression in terms of the Hall algebra. And the claim for me is that the vertex algebra that I'm writing down plays nicely with the Hall algebra via some kind of duality.
But then if I take some modulus this one well. This sum of this modulus is a super nice modulus.
Yeah, that's correct. So
is that your vertex algebra that identifiable with something?
Right. So I've only done this computation for the case of moduli of representations of quivers, because that's like a one-dimensional category, and when you go higher, you have to start worrying about virtual versus non-virtual classes, blah blah blah, and for quiver moduli, what happens?
But this is.
Isn't it quiver moduli?
But you use quiver. I think you can quiver without relations.
No relations. No relations. Yeah. No relations at all. Once you have relations, you get something more complicated. So if you just have a quiver with no relations whatsoever, no superpotential, nothing, it's really just a quiver, and you look at the moduli stack of its representations, then in the homological case, so for the original setup, there's some claim which maybe I'm not so much an expert on, but maybe Yuji can tell everyone. There's some claim that if instead of thinking about the moduli stack, you think of the whole derived moduli stack for the derived category of quiver representations, the associated vertex algebra, there is really some lattice vertex algebra. And when you pass from the derived stack to the original stack, you get some kind of truncation in each component. And I don't know precisely what that truncation is, but it's just some truncation at each piece of your lattice vertex algebra. And the same statement holds inside equivariant K theory. So you'll have some notion of additive, some notion of usual lattice vertex algebra, but now you write everything multiplicatively, and maybe you have some equivariant weights inserted somewhere. And I'm 99% sure that if you just do the usual derived stack business of quiver representations, you'll get some kind of multiplicative lattice vertex algebra. In here. Here.
Yeah, right. No, even further out.
Here.
Yeah.
Yeah. So what's the way to say this? I don't know of really a good way to say this beyond saying that whenever you think about objects like this, you can act by some scaling on one of these factors, leaving the other factor alone, kind of like what you do for Nakajima quiver varieties. And so this thing has a weight with respect to that action. And so when you look at the localization contributions, like when you take Euler class of this, that weight becomes that Z for month.
Oh yeah, then we get powers of that because we get something closer.
That's right. So I did omit a few details, but I mean somehow have to achieve a balance between how many details versus
So here you're mentioning completely basic question. So if you look at coherent sheaves with compact support, nothing would depend on any choice of variant parameters whatsoever. No reasonable stability condition I think you could put on would depend on any kind of invariant.
So it's
points on the three poles.
Yeah.
Then your action, your total points of 16.
I know, but not stability.
the stability condition doesn't depend on equivariance. Yeah. So
Stability and invariants are just
these are
Right.
two separate things.
So, on the other hand, your reverse, if you were to look at a vector bundle or something, then there's no stability condition at all. I mean, unless you do something fairly fancy. Because it's
Sorry, I'm
the mass of it
not
is
exactly following.
on a non-compact state, right? Like an alien surface. You have to do something pretty fancy to write down any kind of stability. Like, I think that the stuff in my paper are stability conditions for vector bundles, but generally don't have it. So, because it does not, what are you going to do?
I mean,
so the surface is just like that with the just horizon.
But like a central charge function in a
I'm not thinking of things. I'm not thinking of things like Bridge stability. So I'm really thinking about stability conditions on the abelian heart of something. I mean, of course, you can think more generally. You have some larger derived category and some stability conditions on there. And as you change those stability conditions, the heart will move around. Right? And that's not the kind of thing that I want to do here. Here I really just have some heart. It's fixed once and for all. And on this heart, I have some notion of stability. I'm not sure if that addresses your question. Yeah, that's a great question. If anyone can tell me like the physical meaning of anything that I've said in the last 2 hours, that would be great. I don't know what this vertex algebra means. I don't know where it comes from. I mean, it's just the fact that you write down these formulas and some vertex algebra pops up.
This might just be a restatement of something. So like you described something that holds like pretty big generality.
That's right. Yeah.
If you specialize something to like really nice, like
Uh-huh.
sheets on answer, you think your vertex algebra will. So you sort of like show that like formally you have one. But
Right.
will it be a known thing?
Yeah, that's a good question. So for every question that you ask me, I can always ask the same question in the original homological setup of Joyce.
Sure.
And so presumably to answer those kinds of questions in my setting, you should first try to work out how it works additively without all these complications with equivariants and like multiple covers. Yeah. So I don't know too much about the Joyce stuff either.
Something doesn't do many examples, so it's easier to.
Yeah. So part of the reason that there aren't many examples in this whole Joyce machinery is really that there just aren't many examples. It's not like sorry. Yes. Of course, those exist, but we don't know how to compute them. Yeah, what's hard is that at some point you want some pullback of some sheaf along some kind of direct sum map. Some kind of direct sum.
Okay.
Yeah. And there, I mean, of course, if you pull back the structure sheaf along direct sum, it's still a structure sheaf. But like you start off with something more complicated, maybe with non-trivial weight with respect to Z. Yeah. And you pull it back, and the Z dependence can change. Like maybe you started off with something of Z degree 1, and you end up with something of Z degree 3 tensors something of Z degree like 2 or minus 2 or something, right? I mean,
maybe the example that we do now, I think it would be really great to have some examples. Like quivers with no relation, let's do a quiver with no relation. Like I don't know. Any.
Yeah,
Actually, a great example is if it's not too simple. It's just one node and one arrow. One cell. I don't. Here it's on C.
Yeah, so that's something that I'm not going to be able to do off the top of my head.
Okay, but it's just. Okay, then I was wondering if we should move the second call to Wednesday. But if we do it by Friday, well, here she's on C. So
But before that, before. Is that?
Point.
What do you mean a point? It's like
Okay, no,
coherent sheaves on a point.
Yeah, it's just vector bundles. There's one component in every integer.
Right. I mean, yeah, but that I can actually write down for you right now, really quickly.
Or do you want to move it on Friday?
How about we have a talk on Wednesday and then see if we need to talk on Friday?
Okay, so good. So then Patrick is in charge of finding a time for Wednesday.
With that, since Henry